Hello everyone, in this video we're going to talk about midterm review part 2 where we discuss atoms and the periodic table and water properties and different types of bonds. So we're going to start with the concept called molecule versus compound. When you look at something such as H2O and hydrogen H2 or oxygen O2, you can categorize it in two different categories, something called molecule versus compound, and sometimes they're material that's neither a molecule or a compound. So here's how this works, okay? So there's something called an atom. When you look at a periodic table, anytime you have something taken directly from the periodic table, that is called an atom. So for example, if you look at this periodic table right here, if you just have P, or if you just have S, sulfur, if you just have F, fluorine, that one individual unit that you can get is called an atom. Once you put different atoms together and make them stay together for a pretty long time, right? They're stable, they stay together for a while. Then you have something called a molecule. So anytime you have more than one atom, you will call it a molecule. So a molecule is a pretty big category still. Molecule and atom are two very different things, right? Atom is just one atom. Molecule is multiple atoms combined together using chemical bonds. And here's something called a compound. The difference between a compound versus a regular molecule is that a molecule is not always a compound, but a compound is always a molecule. What makes a compound special is that it has to have more than, or at least two different kinds of atoms, right? So for example, if you have H2, that's two hydrogen atoms bonded together using covalent bonds, but in the end, they're still hydrogen atoms, right? So this is only a molecule. A compound needs more than two types of atoms, or two elements, you can say. So for example, H2O has hydrogen and oxygen at the same time. Then you will call it a compound. So if we were to put it into circles and really categorize it, you would always have a bigger circle for molecules. There are more molecules than compound existing, right? All of these guys over here, they're all molecules because they all have more than one atom, or more than one atom for sure, right? But what makes these compounds and molecule at the same time is that they have not just more than two atoms, but they also have more than two elements, right? CH4 has carbon and hydrogen at the same time. Sodium chloride, which is salt, has sodium and chloride and chlorine elements together, bonded together. So that's a compound. And you can look at this definition. A compound is a molecule that contains at least two different elements, meaning two different types of letters from the periodic table. So let's take a look at the question. Once you figure out these concepts, we can look at the questions. What is an example of a substance that is a molecule but not a compound? Let me give you an example. O2 is an example. You will, of course, read this as a subscript. And then H2, right? So the idea here is that it's a molecule, not a compound, so it has to be the same element, right? Cl2, something, right? Right? All of these will be called a molecule because it's all the same element. You have two atoms of chlorine bonded together. That makes a chlorine gas, which is a molecule. A substance that is a molecule and a substance, I might count. This is so bad. Please change this on your paper. A molecule and a compound at the same time. So that will be H2O, CO2, CH4, C6H12O6. Right? These all should be subscripts, and you know that already. What else? We could do. I'm blanking. Oh my goodness. All right. Oh, so sodium chloride. Okay, here we go. Right, salt. All these are examples of a molecule and a compound at the same time because they have more than one kind of element. So what is an example of a substance that's neither a molecule nor a compound? That will be just an atom, right? Helium is just an atom on its own. Iron is just an atom on its own. You could also have silver, for example. Let's do silver, right? This is just an atom on its own. It's not bonded with anything. Is a molecule always a compound? The answer is yes. No. I'm so sorry. Is a molecule always a compound? The answer is no, right? Everything that's not just one atom could be a molecule, but it's not always a compound. But a compound is always a molecule. right? Even if you were to have more than two elements bonded together, you definitely would have more than two atoms, which makes it a molecule, right? So let's write down this definition. Does it say? So a molecule is more than two atoms bonded together, and a compound is more than two elements bonded together. All right. So let's take a look at the next question, subatomic particles. When we look at an atom, you need to know what exactly make up the atom, right? When you look at any atom at all, anything on the periodic table. So what are the three subatomic particles that make up an atom? So this will be an atom. You have 3 protons, 4 neutrons, and 3 electrons. So that's the 3 particles. We have protons, neutrons, and electrons, and the charges are protons are positively charged, electrons are negatively charged, and neutrons are neutrally charged. Electrons, unlike this pictures, are incredibly small compared to protons and neutrons. Let's take a look at the questions. Protons, neutrons, electrons for the first question. What makes up the nucleus? So the nucleus is a very dense region at the very center of an atom, and made out of protons and neutrons together, and the electrons kind of swings around actually pretty far away from the protons and neutrons in terms of the scale. And then the charge of one proton is +1, charge of one neutron is 0, charge of one electron is -1. Moving on to our periodic table. So from the periodic table, you can get a lot of information out of it. Okay, when you look at the periodic table, you need to know what kind of information you can extract to answer questions. So let's take aluminum as an example, right? When we look at a periodic table, you always see an atom, and the name of that atom is written. The name of that specific element, is written in the center of these little boxes. And then you would have a number in the corner that's generally a smaller number. That is what we call an atomic number. And you want to write that down somewhere, okay? How to label a periodic table. That is the atomic number. The atomic number, I'll type this one down for you. So what's special about the atomic number? The atomic number equals to the number of protons, right? How would you know how many protons 10 over here has? It's 50 because it's always the same as the atomic number. That's what makes 10 10. The number of protons also equals to the number of electrons if the atom is neutral, right? Under normal conditions, if this atom is neutral, it has 0 charge because electrons and protons are opposite charges, right? Protons have positive charge, has a positive charge, electrons has a negative charge. So protons and neutron should be the same number if you want a neutral atom, right? So if we want a 10, I completely lost it. Oh, 50, right here. If you want a 10, that 10 atom that is neutral, you have to have 50 protons, 50 positive charges, along with 50 negative charges, which is 50 electrons. And then we have something called the atomic mass. So the atomic mass is the number on the bottom that is generally a number with some decimals, right? So for aluminum, the atomic mass is 26.98. That means that's how much it weighs, right? The atomic mass is how much this atom weighs, and how do we calculate that? The atomic mass equals to the proton number plus, plus the neutron number. The reason why we're not adding the electron numbers is because electrons are very small and they're very light. So when we look at the atomic mass, we're really only considering the number of protons and the number of neutrons, right? So once you remember these two equations and understand how we came up with it, then you can answer a lot of questions. So for example, A says, what is the relationship between protons, neutrons, electrons, right? This is the relationship right here, and you can use this to calculate. What is the number of atomic number of a given element? So for example, if we look at aluminum, the atomic number is 13, all right? What is the atomic mass of a given element? So according to the periodic table, is 26.98. And you can just write directly 26.98. And we'll talk about why it's a decimal in a little bit when we talk about isotopes. How many, if you were to write 27, it wouldn't be wrong, but 26.98 is a more accurate answer. How many protons does this element have? So here we go. The proton number equals to atomic number, right? So that means an aluminum will have 13 protons. If you have 12 protons, it will no longer be aluminum. It will be magnesium instead, right? The proton number is what defines an atom, an element. You should never change the proton number. Okay, remember this. We've talked about this in class before. Proton number never changes. How many neutrons does this element have? Neutron number, as you can see, when you add proton and neutron number together, you get atomic mass. So if you were to calculate the number of neutrons, you would make this equation: atomic mass minus number of protons. Right? But here's the problem. The atomic mass has a decimal. When we calculate the number of neutrons, clearly we can't have 0.98 neutrons. That doesn't work, right? It's as if you can't have 0.5 of a person. That's not how a person works, right? So in this case, we will round 26.98 up because 26.98 is larger than 26.5. If you have 0.5 and above, you will round up. In our case, at least. So 27 is our atomic mass, or our rounded atomic mass, minus 13, which is our atomic number, which is also the same number as the number of protons, and then we have 14. So we know that this element should have 14 neutrons normally. Okay, how many electrons does it have? If the element is neutral, the answer should also be 13. Now, so normally the number of electrons should be 13. But what would happen if this element has a charge, right? If it has a -1 charge, you know that electrons carry negative charges. So if you have a -1 charge, that means instead of having 13 electrons, which makes it neutral, you will have an extra electron, which makes it 14 electrons, right? If you were to have a -2 charges, that means you have 2 extra negatives, and you can just think about negative as electrons. So instead of having 13 electrons as you normally would, now you would have 15 electrons. And then if you were to have a +1 charge, that means, well, you can't gain protons, right? Protons are positive charges, but you can't really gain protons because proton number never changes. If you change the proton, it's no longer the same atom. So what do? You can take away electrons, right? So if you have a +1 charge, that means instead of having 13 electrons, you would have 12 electrons. And then for the last one, if you have a +2 charge, that means instead of having 13 electrons, you would have 11 electrons, right? Not all these cases actually happens, but my point is if you're having negative charges, you want to add more electrons than the regular atomic number, and if you were to have positive charges, you would take away electrons. Lastly, would the number of protons change for an ion? An ion is anything that carries a charge, right? All of these guys will be an ion. If we were to do aluminum, Al, with a -2, that's an aluminum ion, right? But the proton number never changes. You can't change the proton number, otherwise you wouldn't be aluminum anymore. The next concept that a lot of students have troubles with is called isotopes. So what an isotope is that they're basically different variations of the same atom, or the same element, okay? So the idea is, for example, if you were to have ice cream, right? Ice cream is just ice cream. Ice cream is not celery. Ice cream is ice cream. But ice cream has different flavors. You can have chocolate ice cream, vanilla ice cream, but in the end, they're still ice cream, right? Same idea with elements. If you have hydrogen, in the end, it's hydrogen. It will have one proton. That's what makes a hydrogen. But you can have different flavors of the same hydrogen. By flavor, I mean it will have different numbers of neutrons. So for example, right here, we have hydrogen 1, which has the atomic mass number of 1. So have one proton and no neutron, right? If you were to have hydrogen 2, that means the atomic mass is 2. That's what this dash means. If it has hydrogen 2, you have hydrogen 2. Proton number is still 1 because that's what makes a hydrogen. But instead of having 0 neutron, you would have 1 neutron. Together, you would have proton plus neutron, 1 plus 1. The atomic mass is 2. And then in comparison, you can also have hydrogen 3, which means the atomic mass is 3. Again, we have 1 proton always. 3 divided by 1, you have 3 divided by 1, you have 2 neutrons, right? So that's what makes hydrogen 3 hydrogen 3. But in the end, again, it's a hydrogen. It just has a different numbers of neutrons, which gives it a different number of a different atomic mass. Another example would be carbon, right? Really, every element has different variations of it. So we have carbon 12. Carbon 12 means it has an atomic mass of 12, but carbon always has 6 protons, because if you look at the periodic table, carbon has the atomic number of 6. So carbon 12 has 6 protons and 6 neutrons, but you can also have another variation of carbon called carbon 13 with 6 protons, 7 neutrons, and carbon 14 with 6 protons and 8 neutrons. As you can see, the proton numbers are always the same, and the neutron numbers can vary, okay? And this is something that naturally occurs. It's not, a definition that we gave. This is what we observe as scientists. So here comes the thing, right? Why is it that when you look at a periodic table, instead of having a full number, an integer, you would have decimals behind the atomic mass, right? So the reason for that is that there are different variations of the same element, and we're kind of getting an average of all the variations, right? So for example, we're looking at this magnesium. There's magnesium 24, 25, 26. They all have 12 protons, and this would have the atomic mass of 24, which means the number of neutrons will be 12, number of neutrons will be 13 and 14, right? But the percent abundance is different, meaning that how much of each type of magnesium do we have in nature? We find out that about 78.99% of all the magnesium in the world are the kind of magnesium that weighs 24, called magnesium 24, right? And what you do is that you take this abundance, 78.99%, times the atomic mass, which is close to 24, and then you do the same thing, and then you add them together, then you would have an average atomic mass of 24.31. It's the same idea of calculating your grades for the class, right? If you have 90% on exams, a 90% average on exams, but the exam only weighs 40% of the grade, you will do 90% times 40, and then let's say the rest of it is quiz grade, so 60%. And then you would do, let's say your quiz percentage is 80. So you do 90% times 40% plus 60% times 80%, right? So I hope that makes sense. If this is still difficult for you to understand, make sure you ask in class tomorrow. At some point before the midterm, right? You got to figure this out. I guarantee you, if this is difficult, if I think you don't know it, I'm probably going to ask you this question just to make sure you know it, right? So let's take a look at the questions. What are isotopes? Isotopes are variations of the same element that has the same number of protons and different numbers of neutrons. So then we can answer these questions. Do isotopes of an element have the same numbers of protons? The answer is yes. They always have the same number of protons. That's what makes an element different from another element next to it on the periodic table. Do different isotopes of an element have the same number of neutrons? The answer is no, right? Different neutrons numbers is what makes the elements, or the isotopes different from each other. The electron numbers can change no matter what, right? We can take away electrons, give it electrons, but that doesn't make it an isotope, right? So here's something that people often get confused about. Well, what about the electrons? The electron changing doesn't influence an isotope. If you have magnesium 24, you can have 12 electrons, 13, 14, doesn't matter as long as you have 12 protons, 12 neutrons, that will make magnesium 24. All right, how do you know which isotope is the most abundant in nature when you look at the atomic mass, right? You would, whichever atomic mass that is of an isotope is that is closest to what's shown on the periodic table should be the most abundant, right? So think about this. If you have an exam average, well, let's say you take 3 exams, one you get a 90, the other 2 you got a 60, and a 50, right? Your exam average is going to be closer to the 60 and the 50 instead of the 90, right? Because, well, you get the 50 and 60 lower grade more often than the 90, right? This doesn't happen to anyone. But the idea is, the more abundant something is, the more weight that this one type of thing is going to take up in the average, right? So So for example, just by looking at aluminum over here, for example, I said example twice, you would already know that aluminum 27, the aluminum that has the atomic mass 27, which has the proton number of 13 and the neutron number of 14, that will be the most abundant type of aluminum in the world. All right, moving on. Half-life. Half-life is another roadblock for a lot of people, right? So let me demonstrate half-life by tearing up yet another paper. Okay, let's see. This looks like a good paper to tear up. We have this red paper, okay? This is, you can think of this as an unstable, this paper is unstable, right? So with different types of isotopes, some of them are more stable, which is what makes them exist more often in the world. And there are other ones that are not so stable, and they will become other types of elements. They will literally, right, misbody turn into a unicorn kind of thing. Not exactly, but you get the idea. So here's the thing. Let's say you have all these, you have 100% of these unstable elements. After one half-life, let's say this one half-life is 5 seconds, right? This means after one half-life, 5 seconds, half of the total amount is just going to be gone, right? So now you only get 50% left after one half-life, right? So half-life is literally the amount of time it takes for half of the radioactive isotopes to go through radioactive decay and become a different type of element, okay? So if you go through 2 half-lives, 10 seconds, you would have this paper, and we do this once again. So instead of having 1/2, you get 1/2 of the 1/2, and so now you have 1/4 of the paper left, right? And then you do this again. After 15 seconds, 3 half-lives, because 1 half-life is 5 seconds, 3 half-lives, you times 3, 15 seconds. Now you only have 1/8 of the paper left, right? We can keep doing this. 20 seconds later, we have 1/16. 25 seconds later, we have, I can't math anymore, 1/32 for 32nd, okay? So if you look at so let's see, let me give you a good definition of half-life. Half-life is the amount of time it takes for half of the amount of radioactive atoms to decay. Okay, decay meaning it becomes a different type of element. You don't really need to know how it works until you learn chemistry next year. So here's a question. If the half-life of a substance is 20 years, how much of the substance will be left after 60 years, right? Think about this. You have 100%. After 20 years, you would have 50%. After another 20 years, now you're on down to 40, you would have half of that. So you have 25%. And then after another 20 years, you will get half of that. So 12.5%, right? 5%. All right. So same idea over here. If you look at this picture, after each half-life, you get half of the original amount left over. Okay. So you really got to think about this. Maybe tear up some papers until you understand this, because you gotta. All right. On to the next one. Now we're going to talk about chemical bonds. There are different types of chemical bonds because different types of elements interact with each other in different ways. So there's something called electronegativity. The electronegativity is how much an atom is attracted to the electrons around it, okay? So sometimes you have elements that are very attracted to electrons. It's just going to catch it, it's going to take it, it's going to keep it forever. And then there are other types of atoms that don't really like its electrons. It doesn't have a lot of attraction for the electrons. So sometimes the electrons will wander off and go somewhere else. Well, if one atom wants to give away its electrons, one wants to take some electrons, and you put the two together, that is a perfect match, and they're gonna form some bonds, okay? So here are the different types of bonds. There's one called an ionic bond. An ionic bond is when one atom has so much attraction force for these electrons, and one atom has so little attraction force for its electrons that certain electrons from one atom will literally fly away to the other atom and become a part of it. And together, this molecule will form an ionic bond. So for example, we have sodium chloride, which is salt. Sodium has 1 valence electrons, and if you remember the octet rule, elements either want 0 or 8 electrons, right? Getting 8 is wonderful. Chlorine has 1, 2, 3, 4, 5. There are 2 more on the inside. So actually, this is wrong. There should be 1, 2, 3, 4, 5, 6, 7. Okay, chlorine should have 7. So if you already have 7, you want 8. Sodium and chloride together, 1 electron is going to be transferred over from sodium to chloride completely. The sodium loses an electron, right? So in this case, you'll form an ionic bond. When one atom loses 1 or more electrons, the other one gains, right? Okay, so the result is, in this case, for example, you would have sodium with a plus charge because it lost an electron. It has 1 less electrons than it normally would, so it would have a positive charge, and then you would have chloride ion, which has a negative charge. Then the next one is called a covalent bond, right? So an ionic bond is when the electronegativity of the 2 atoms are very, very different. Covalent bond happens when the electronegativity of 2 atoms are pretty similar, right? So if 2 atoms don't really want to give away an electron completely or gain an electron completely, then they will share, right? This is a great moment as well. So for example, if you were to have hydrogen and another hydrogen, they are the same element, so they will have the same type of attraction force, same amount of attraction force for the electrons, no matter what, because they're the same, right? So this will result into something called an equal share of electrons. They're not only sharing, the sharing is completely equal, right? So let's say I have these 2 hands, we're sharing this paper to the same degree, right? It's right in the middle. The electrons are right in the middle of these 2 atoms. This is called a nonpolar covalent bond, which is what we call equal share of electrons. You can still share, but it doesn't always have to be equal, right? If this hand is a lot stronger than my other hand, and it pulls the electrons to the other side, they're still sharing, but it's an unequal share. So in that case, we call it a polar covalent bond, where we say this type of molecule that has a polar covalent bond, we say this type of molecule is polar, right? Here's another picture that shows you. If we have equal share of electrons, chlorine, they're the same type of element, they have to have equal share because they're the same, right? So these electrons that they're sharing in the middle will be right in the middle. This is a non-polar covalent bond. If you were putting hydrogen and chlorine together, they have pretty similar electronegativity, but not similar and not the same, right? So the idea is that because chlorine has a little more electronegativity, it wants the electrons, or it has more attraction force to the electrons, just a little bit more than the hydrogen, then the electrons will be shifted toward the chlorine. That is called a polar covalent bond. And then we have the ionic bond. If the chloride is so much more attractive to electrons than the sodium right here, then it will just snag away the electrons. Then this type of bond is called an ionic bond, is when you have a complete transfer of the electrons and you have a full charge.